Greetings, linear algebra students. Today we're going to talk about orthogonal sets. And you learned a little bit about these already in the video. We're going to see how these help us find the next best thing to a solution when we have inconsistent systems. But that will come next week. So in the video, you saw the orthogonal set couple properties that are linearly independent. And you'll also learn how to solve a matrix equation when A's columns form an orthogonal set. In particular, you saw theorem 4, which says that orthogonal sets of non-zero vectors are linearly independent and hence they form bases for their spans. And so let's talk about why that is first. So we're going to start by looking at that linear independence result, or linear independence equation, I should say. C1U1 plus C2U2 up to CPUP equals 0. Now what we want to show is that C1 equals C2 equals C3, etc., all the way up to CP, that those are all 0 for these to be linearly independent. We want to show that's only the trivial solution. So how are we going to show that? Well, we're just going to take any one of the vectors in our set, in our orthogonal set, and dot it with both sides. And take UI dotted with the left-hand side equals UI dotted with the 0 vector. So we can distribute that and say C1 UI dot U1 plus C2 UI dot U2 up to CP UI dot UP equals, on the right-hand side, we'll just get 0. Now on the left-hand side, UI is orthogonal to every vector except for itself in that set. So almost all of these dot products are going to be 0 except for the ith one. So the left-hand side is just going to be CI UI dot UI equaling 0, or CI magnitude of UI squared equals 0. Now these are non-zero vectors, so this magnitude is not going to be 0. So the only way this can be 0 is if CI is 0. And that's true for every I. It's true for I equals 1, I equals 2, so C1 is 0, C2 is 0, etc. And that's the way we get there all 0, so that's how we get there linearly independent. The other result you saw was that if I have an orthogonal basis for W, some subspace of my vector space V, then we can solve the equation C1U1 plus C2U2 up to CPUP equals Y with CI equaling Y dot UI over UI dot UI for I equals 1 through P. So why is that? Well, just take that equation. We know that Y is written as a linear combination C1U1 plus C2U2 up to CPUP equaling Y, and let's just dot both sides with UI. So we're going to get C1 U1 dot UI plus C2 U2 dot UI up to CP UP dot UI equals Y dot UI. Again, we have UI dotted with anything other than UI is 0 because it's an orthogonal set. So on the left-hand side, we get CI UI dot UI equals Y dot UI. Again, UI dot UI is really just the same thing as the magnitude of UI squared. These are non-zero vectors. It's an orthogonal basis, so none of them are the 0 vector. And so because of that, we know that UI dot UI is non-zero, so I can divide by it. And I get CI is Y dot UI over UI dot UI, as stated in the theorem. So we don't even need to row reduce a matrix if we have orthogonal columns. We can just solve an equation by computing each of the coefficients. So I'd end up with some solution where I'd have a vector X whose entries all have that form. That's kind of nice. I don't do any row reduction to solve. Now this should look familiar from physics, maybe calculus, depending on if you discussed it in your calculus course, but this should look familiar. These are projections. So let's talk about that. If you haven't seen that before, it's totally fine. Let's say that we're going to say let y and u be in Rn where u is not the zero vector. So the picture I'm going to have here, here's u, here's y. So I just drew these two vectors kind of pointing in different directions, emanating from the same point. And if I imagine taking a flashlight and shining it perpendicular to u, and try much perpendicular lines to perpendicular to u, the shadow that the vector y casts onto u is going to be what I call my projection. So if I think about kind of projecting here, I'm going to have this kind of shadow that y casts on u. I'll call that the projection of y onto u. So u is a subscript. And we'll also often, at least when there's not, when I'm just working with a single projection, a shorthand we often use is y hat. But if we're working with a lot of projections, then we have to be more careful with our notation. One other vector that appears in here is the vector from the end of y hat to the vector y. I can draw it coming from the same point that y and u are coming from, or I can draw it coming from the end of y hat. But that's the vector from y hat to y, so it's just really y minus y hat. Now, a couple observations. First, y hat is parallel to u because I projected onto u. It's a shadow on u, so it's pointing in the same direction as u. If y is actually pointing, it's possible it's in the negative direction depending on where y is pointing, but it is going to be a scalar multiple of u. And the other thing to notice is that u and y minus y hat are orthogonal. So for us, what does that mean? That means that y minus y hat dot u equals 0. But that's y minus cu dot u equals 0, or y dot u minus c times u dot u equals 0, or y dot u equals c times u dot u. Again, a product of a vector with itself is just the magnitude of that vector squared. So because u is not the zero vector, this expression u dot u is not 0 either. So this tells me that c is y dot u over u dot u. And so y hat has the form y dot u over u dot u times u. So a couple other just things to note. Now this one looks a little silly. Y is clearly y hat plus y minus y hat because the y hats cancel. But I'm going to view a vector in this form because I'm kind of decomposing it into a vector that's in the direction of u and a vector that is then perpendicular to u. So this is in the span of the vector u, and this is orthogonal to u. And we can imagine, we can kind of think of the length of y minus y hat, the length of this vector here is kind of representing the distance from the vector y to the span of the vector u. Let's just do a little example. If I have the vector y is 1, 4 and u is 5, 5, then I can compute y hat is going to be y dot u over u dot u times u, which is 5 plus 20 over 25 plus 25 times 5, 5, giving me 25 over 50 is a half times 5, 5, giving me 5 halves for my projection vector. I can, if I wanted to, I could say y minus y hat is 1, 4 minus 5 halves, giving me negative 3 halves, and then positive 3 halves. And I can check if I take u dot y minus y hat, I get 5 halves dotted with negative 3 halves, positive 3 halves, which is 0. So it's really R orthogonal. Now let's go back to that expression from theorem 5. We said that if we had, again, U1 through UP was an orthogonal basis. And I wanted to write y as a linear combination of U1 through UP. Well, one thing we could always go back to the beginning of this course and we could row reduce a matrix with columns U1 through UP augmented with the column y and then solve. But we now know that there's something better to do because these are orthogonal. We know that this is y dot U1 over U1 dot U1 times U1 plus y dot U2 over U2 dot U2 times U2 up to y dot UP over UP dot UP times UP. This should look familiar. These are just projections. So this is going to be, first we're projecting y onto U1, and then we're adding on the projection of y onto U2 up to the projection of y on to U sub p. And so let's just draw a picture. I'm just going to use U1 and U2 just because it's easier to draw things in 2 dimensions. So let's say I have a set of 2 orthogonal vectors. So geometrically, it just looks like 2 vectors that have a right angle between them. And let's say I have some vector y. Then what I'm saying is that if I want to write y as a linear combination of U1 and U2, I know how to do it. I'm going to first project y onto U1. And then I'm going to project y on to U2. And now y is the sum of those 2 things, which I think makes sense. You're going along this vector, then along this vector to get to y. So you're just traveling along those projections. Now, what we're going to be doing with some of this stuff very soon is if y doesn't happen to be in the span of the columns in the column space of a matrix A, and I'm trying to solve AX equals Y, I'm going to use certain projections to help me find the next best thing to a solution. For now, though, the rest of the time on this section, I want to focus on the special case of an orthonormal set. And an orthonormal set is really just an orthogonal set where every vector has length 1. And such a set is still going to be linearly independent because it's still orthogonal. I'm just changing the lengths. Like, so I have a bunch of orthogonal vectors, maybe they're longer or shorter, and I'm just scaling them so they're all 1 now. So still linearly independent by theorem 5. Hence a basis for this subspace it spans. We'll use the term orthonormal basis to describe an orthogonal basis where every vector has length 1. Now, it's really easy to create. If you have an orthogonal basis or orthogonal set, it's really easy to create an orthonormal one. All you do is scale each vector by its magnitude. So this first vector, 1, 2, -1, you saw in the video, you saw the set 1, 2, -1, 0, 1, 2, and -5, 2, 1 was already orthogonal. You can check that in your own if you want. But the length of 1, 2, -1 is a square root of 1 plus 4 plus 1, or square root of 6. The square root of the vector 0, 1, 2 is a square root of 0 plus 1 plus 4, or square root of 5. And the square root of 25 plus 4 plus 1 is the length of the last vector, so it's square root of 30. And so if I want to create an orthonormal basis, I'm going to take the first vector and scale it by 1 over root 6. Take the second vector and scale it by 1 over root 5. And last one, I'll scale by 1 over root 30. And I have my orthonormal basis. Now, what's really cool is that matrices whose columns form an orthonormal set have a number of really interesting properties. So theorem 6 says that if I have an M by N matrix U with orthonormal columns, it's going to have orthonormal columns if and only if U transpose U is the identity matrix. So this is kind of cool because notice that U is not necessarily square. And because it's not necessarily square, it's not necessarily invertible. So this is, it's not like this goes both directions. It's U transpose U, not the other way around. So let's just talk about why this is. Let's just use a matrix with 3 columns. And let's call those columns U1, U2, and U3. So U transpose is going to be a matrix with 3 rows. And those rows are the transpose of the first column of the first matrix. The second row is the transpose of the second column of the original matrix. And the third row is the transpose of the third column of the original matrix. So if I look at the matrix U transpose U, if I use the 1, 1 entry as row 1 of U transpose, dot it with column 1 of U. So it's going to be U1 transpose U1 for the 1, 1 entry. The 1, 2 entry, very similar, row 1 dot column 2, so U1 transpose U2, and we can continue. We'll have the IJ entry will be UI transpose UJ. Filled in all those entries where the IJ entry is UI transpose UJ. Now remember that UI transpose UJ is the same thing as UI dot UJ. So all of the off diagonal entries are 0. Now the diagonal entries are U1 transpose U1, U2 transpose U2, U3 transpose U3, that's U1 dot U1, U2 dot U2. Remember that UI dot UI is the magnitude of UI squared, which in this case, because they're orthonormal, is 1 squared, or 1. Okay, so the columns of U are going to be orthonormal if and only if we get these entries to be 0, and they're going to be orthonormal if and only if these entries are 1. And so this is why it kind of goes both directions in this result. So it's kind of cool because we don't usually think about having, like, we often not think of having that the inverse helps us get I, but now in the case of a matrix with orthonormal columns, the transpose helps us get the identity. Now another nice result is that if I have, again, use an M by N matrix with orthonormal columns and X and Y are vectors in Rn, then there's kind of 3 things I can say here. First, the length of u times x is the length of x. Now, let's talk about why that one is true. I'm going to start off by taking ux and just taking its square, the magnitude squared, which is the same thing as ux dotted with ux, which is ux transpose ux, which is x transpose u transpose ux. U transpose u is I, giving us x transpose x, which is x dot x, which is the magnitude of x squared. So the square of this is the square of this, but because they're both positive, we have that those two things are equal. Now let's just try and interpret what's going on here. So what we're saying is that if we're thinking of the matrix transformation where I take x and map it to ux, this tells us the transformation t of x equals ux preserves length. If I have a vector of length 5, its image is going to be a vector of length 5, which is something we don't usually have happen for most of our transformations. Now the second result says that ux dot uy is x dot y. Okay, a very similar argument. Ux dot uy is ux transpose uy, which is x transpose u transpose u y. Again, u transpose u is I, so this becomes x transpose y or x dot y. So let's think about what this means. Again, now this is a little, we have to think a little more deeply about what's going on here. So if you go back to physics or calculus 2, remember the dot product tells you about angle. In particular, you can use the dot product to compute the exact angle between two vectors. So the fact that the dot product's maintained, so we can say t of x equals ux preserves dot product, which means it preserves angle. So if two vectors that are at a particular angle, they're going to be transformed to two vectors that have the same angle between them. And then the last one is really kind of a special case of that. But ux dot uy, oops, I put it in the wrong spot. Let's put it in the right spot. Okay. Sorry, ux dot uy equals 0 if and only if x dot y is 0. And that just follows from B. It's really a special case of B in the case that x dot y is 0, right? But again, what you want to think of is if I have two vectors that are orthogonal and I transform them with u, they're going to remain orthogonal. They're just going to kind of like shift around in space somewhere. And just one last thing to close. You're going to see the term, this is one of the very, very unfortunate terminology things. I really wish that we could rename, maybe we should for this semester. But an orthogonal matrix is going to be a square invertible U such that U transpose equals U inverse. So what I want to point out is that it's got to be square to be orthogonal. An orthogonal matrix doesn't have orthogonal columns. An orthogonal matrix, go back up to here, theorem 6, has orthonormal columns. Why don't we call it an orthonormal matrix? Yeah, so note, an orthogonal matrix is square with orthonormal columns. I wish we called it an orthonormal matrix. I guess it's more syllables, maybe. I don't know why it's called an orthogonal matrix, but it's got the property that U transpose equals U inverse. And so its columns have to be orthonormal according to theorem 6. So that's all for today. Make sure to complete your activity, and I will see you all on next class.